Damn. लास्ट बंदा गया घर से बाहर। हाँ, काम के लिए बुला लिया। अच्छे। हम्म।
My number plate.
Hello, everyone. Looks like we've got 36 in here. So before we get started on anything new, did you guys all get the email today that campus is completely shut down? No? Yeah, we got an email. Someone tested positive and they were last on campus not long ago. And so, and right when they did that, I realized I needed to get something out of my office. I was in a group chat with Mariana and Tim and Andy and Doug. And, you know, they're all like, shit, I need stuff too. And so I just asked the dean if I could just sneak over there, and she said, yeah, go ahead. So went over there and nothing. Got my shit and left. But anyway, looks like everything's shutting down. I don't know what my kids are going to do now that the beaches are all going to be closed. All right, so let's see here. Let's share the screen.
Pull out the kiddie pool.
Yeah. Okay. So how about what am I doing here? Do you guys have any integrals that you got stuck on and you want me to do them? I can't see the chat, so when I'm sharing my screen, so if you do, you're going to have to kind of speak up. No? All right. All right, so let's do this improper integral stuff. So, recall, oh, by the way, I was having a bunch of trouble this morning. I got booted out of the class several times. I think where I'm sitting in the house is maybe too many people were using their stuff. But anyways, if I get booted off, I'll try to get back in. And if I can't, I'll put it in the announcements. Okay, so recall that if the function f is continuous on the interval AB, okay, then this definite integral from A to B of our f of x dx, it ended up being the limit as n tended to infinity of the sum, I equaling 1 to n, of f of xi star delta x, where xi star, you know, we've partitioned up the interval AB, and xi star is sitting somewhere in between xi minus 1 and xi. Okay. Now, it was Riemann and I'm actually reading a book about Riemann's paper of 1859, right? That's what I was doing right before I got in here. Riemann was able to prove that this limit converges. Okay. Now, the ideas behind all of this stuff had been around long before Riemann. You know, Riemann is mid-1850s, and people had been integrating nonstop. But we call these things the Riemann integrals because, you know, his development of the subject and how he was able to show that this thing converges right here was kind of important. So a math major, probably as a junior, after you get out of this calculus stuff, you definitely will be looking into that upper and lower envelopes and stuff. Okay, so now, what if f isn't continuous on the interval AB? Like, for example, suppose we wanted to integrate from -1 to 1 x to the -1/3 dx. Okay, now notice that this is the integral from -1 to 1 of 1 over the cube root of x dx, and we have a problem where x equals 0. Okay, but occasionally something like this will just kind of work itself out. If I integrate this, I'm going to get x to the positive 2/3 divided by 2/3 evaluated at -1 and 1. Okay, and because it's a square thing, you know, why is it on eraser? It's going to be 0. Okay, so the singularity at x equals 0 kind of took care of itself. All right, what we want to have happen is something a little more precise. Okay, if we look at a graph of what is happening here, as x is going to 0 this direction, 1 over, like when x is getting really small positive, this thing is getting very large positive. And so it's going up like this. Oops. You know, okay. And then as x is coming in like this, the cube root of negative numbers are negative, and so the function is going down like that. So in a sense, these infinitely huge regions are just canceling each other out. Okay, but it's not always going to work like that. Okay, so let's start with a definition of what we're going to mean by an infinite integral. We'll start with, well, no, we'll stay with this. Okay, so not a definition. Okay, let's suppose that f is continuous on the interval a to c union c to b closed. Okay, so here's a, here's b, c is somewhere in here, and the function is not even defined at that number. Okay, okay, so by taking care of this, we're going to take care of a couple of cases at once. All right, So we define the integral from a to c of f of x dx as equal to the limit as epsilon goes to 0 through positive values of the integral of a up to c minus epsilon, then the f of x dx thing. All right. And then we would define the integral from c up to b of f of x dx as the limit as epsilon goes to 0 through positive values. Okay, now this guy, by the way, I always, when I'm doing these things, I always like to use and indicate the one-sided limits. Okay, so that way I know what I've got. Here's the C right there, by the way. So in order to stay in the region of where we're continuous, we have to go up a little bit. And this is going to go to B, okay, of this f of x dx. And this is provided these limits exist. And what happens with improper integrals, people start getting really lazy with them. Even in this book that I'm reading right now, Gauss wrote the integral from 2 up to x of dn over the natural log of n is behaving like the log of x. Okay. And so, you know, one of the things that Euler was able to establish was that if you add up the reciprocal of all the primes, that this sum diverges. Okay, we'll be talking about this a little bit later. And he said it diverges sort of like the log of infinity. Okay, so generally when you've got these improper integrals, they usually go to infinity right around, you know, these spots here. Okay, and then finally we define the integral from a to b of f of x dx as the sum of these two integrals, which have been defined via a limit. Okay, so people were trying to put as much rigor into this stuff as they could. One of the problems that was, as we're talking about this book I'm reading, around the beginning of the 1800s and certainly through the middle, this distribution of the primes throughout the integers was a big thing, and it took people to like really pin down better definitions of these improper integrals in order to establish what they were trying to get at. Okay, so in that problem that I just did earlier, here's how we would have to properly do it. So the integral from -1 to 1 of x to the negative 1/3 dx. It's going to be the limit as epsilon goes to 0 through positive values from -1, let's see, to here's -1, here's 0. Okay, so I need to be right there. So we're going to go up to 0 minus epsilon, or just negative epsilon. It might look weird with sitting there negative epsilon. Let me erase this thing. Of x to the negative 1/3 dx, and then plus the limit as epsilon goes to 0, again through positive values. I'm now going to go 0 plus epsilon up to 1 of this x to the negative 1/3 dx. Okay. Now, notice that I'm using the same epsilon here. And one day in my complex analysis course at UCLA, I was in grad school with Winnie from the Wonder Years. I was Takasaki.
She actually works there, guys. He's not kidding.
Yeah, she was in my Riemannian geometry class. You know? Anyways, somebody asked Takasaki, like, because Takasaki, well, here's what Takasaki did, okay? He didn't use epsilon in the second one. What he did is he used a different value, like delta goes to 0. Okay, and one of the people in the class, not necessarily Winnie, but one of the people in class asked him, can we just use the same epsilon in both places? And, you know, he just went on a tirade. He said, no, and this is why. And he pulled out all of these bizarre examples that, I mean, to this day, that I get into my notes, I still have all that shit. And it's still kind of confusing. Okay, but for us, you know, you can leave it as the epsilon. All right, so now we just do the integral. Okay, so now it's going to be the limit. Epsilon is going to 0 through positive values. I'm going to just do this all in one shot. Okay, so it's going to be x to the 2/3 divided by 2/3 evaluated at -1 and negative epsilon. Okay, and then plus 3/2 x to the 2/3 power evaluated at epsilon and at 1. And here I'm just going to switch back to my epsilon thing. You'd have to come across a very unique individual to have just sitting there ready to go an example where this doesn't always work out. Then again, Takasaki was I don't even know if he's still alive, but he was quite a character. He had little disciples that followed him everywhere, like 15 of them. And everywhere he went, you could always hear them because they were all walking down the hallway together. And they thought they were so cool. All right. So when I plug in my stuff here, this is going to be the limit as epsilon goes to 0 through the positive values. Okay, so now it's going to be this 3/2, and then it's going to be epsilon, negative epsilon, raised to the 2/3 power minus 3 over 2 when I plug in -1. Okay, and then it's going to be plus 3 over 2 minus the 3 over 2 with the epsilon here going to the 2/3 power. These two things cancel. And so what we get is the limit as epsilon goes to 0 through the positive values. Looks like I'm going to have 3/2, and negative epsilon squared is the same as epsilon squared. And so for this particular problem, we really don't even have to compute a limit because it just wipes itself out. And so there we go. That's about as rigorous of an establishment of that idea as we're going to see. Any questions on that one?
So the limit always goes back to being zero? Or
No, not necessarily. Like, for example, like suppose I wanted to integrate from 0 to 1, 1 over the square root of x. Okay, so this is another one where the singularity just kind of removes itself. But what we would have to do here is we'd have to say, okay, it's the limit as epsilon is going to go to 0 from positive values, from the integral from 0, like plus epsilon. Why don't I just say epsilon there? I think you guys now know what's happening. So this is going to go from epsilon up to 1, x to the -1/2 dx. So that is the limit as epsilon goes to 0 through positive values of 2 square roots of x evaluated at 1 and epsilon. And so this time we actually do need to do a limit 2 minus 2 square roots of epsilon. And for you guys that weren't with me for Math 180, one of the most important things that we said in those early weeks were limits pass through continuous functions, okay? So you can pass the limit all the way through the radical sign all the way and get it. And so therefore, that's going to be a 0, so the answer is 2. Okay? Now, for most of these guys, you probably wouldn't do it like this. You know, you'd probably just go through it. Okay? But sometimes, you know, it's required of you. And for you engineering people, us lazy-ass mathematicians, you know, we get on your ass for not being thorough and doing all this limit stuff, but then look how lazy we are now. Anyway, okay, so there's a new type of, another type of integral that we can consider. Let's suppose that our function f is continuous on some interval from a all the way to infinity, and we want to define what this means. The integral from a to infinity of f of x dx. And for that matter, we might want to do this, negative infinity to a of f of x dx. And for that matter, we might want to even do negative infinity to infinity of f of x dx. Okay? So there really is no discontinuity here. It's just that in all of our definitions and so on, we you know, partitioned a finite interval. Let me shut something off. So we partitioned up a finite interval. Now we have an infinitely long interval. Okay. So the definition of this is going to be as follows. Okay. Definition. If the integral from a up to t of f of x dx exists for all t larger than a, we define the integral from a to infinity of f of x dx as equal to the limit as t goes off to infinity for a up to t f of x dx. Now, generally, when I'm letting a variable go off to infinity, I usually don't go with t. But because I've been teaching out of this book for so long, anytime this improper stuff comes up, I just knee-jerk use t. Okay? All right. So what we're trying to avoid here are situations like this. Like, back in the day, Leonard Euler, he would write stuff like this and call it zero. Okay, this is Euler. Now, the 1800s is the period of time where the foundations of not just calculus, but a lot of other areas of mathematics started getting, more thoroughly gone through. And this whole idea of, infinity is not a real number. And so you can't divide a real number by something that's not a real number. So it was all of this stuff, up here that was happening. For example, this is an interesting problem here. If we want to integrate, let's say, from 1 to infinity, 1 over x squared dx. Okay, so we would write it as the limit as t shoots off to infinity of the integral from 1 to t x to the negative 2 dx. Now this is the limit as t goes off to infinity of x to the negative 1 over negative 1. So it's going to be 1 over x evaluated at 1 and t. Okay, now some of you are saying, hey, hold on. The integral of x to the negative 2 is negative 1 over x. But see what I did here is I switched the orders of the bounds, because there's a good chance if I left the negative in there, I'd lose it. All right, so what we get here is the limit as t goes off to infinity of 1 minus 1 over t. And that limit is 1. So a person could say that the area underneath this curve from 1 going all the way out to infinity is 1. Okay. So what if I had something like this? The integral from negative infinity to positive infinity dx over 1 plus x squared. Okay. So I'm gonna break one of Takasaki's rules here, and I'm going to use the same letter in both the bounds. It's going to be the limit as t goes to infinity of negative t up to t dx over 1 plus x squared. So this is the limit as t goes to infinity of the tan inverse of x evaluated at negative t and t. Okay, so this is the limit as t shoots off to infinity of the tan inverse of t minus the tan inverse of negative t. Okay, so now you need to remember what tangent looks like. Okay, we have selected this region for y equals tangent x, and it lives between negative pi over 2 and pi over 2, and it's going to go like that. Okay, so as x goes to pi over 2, tangent of x goes to infinity. So that means that this is going to be pi over 2. Okay, minus. Okay, now what happens as the arguments go here? As x goes to negative pi over 2, tangent of x is going towards negative infinity. Okay, so that would be negative pi over 2, which we get as pi over 2, pi over 2. And so we get pi. Okay, so that's kind of interesting that if we were to graph this function, it's going to look sort of like a bell curve. Okay, and it's going to go. We could use all of our Math 180 stuff. Come on, draw. It's on draw. We could use all of our Math 180 stuff to figure out, where the points of inflection are and stuff like that. But as long as I didn't make any mistakes, the area is equal to pi. Okay. Try another important example here. 1 to infinity of 1 over x dx. So that's going to equal the limit as t goes off to infinity of the natural log of t minus the natural log of 1, but that's just 0. And that is plus infinity. So when we were last semester talking about the logarithm and stuff like that, and we got to L'Hopital, we were able to characterize the logarithm a little bit better. The logarithm is the function, the elementary function that goes to infinity the slowest. Okay? One way of thinking about the logarithm is this. If I was to, and Eduardo, you will look at sequences of functions when we get to be a junior. This might be the, why is it doing that? So I'm here. This would be like the square root of x. This function might be the cube root of x. And then this guy here, the fourth root of x, and so on and so forth. Sitting underneath all of these guys is this logarithm function. Okay. Now there are occasions where the logarithm function will hit some of these graphs and then cross right back over them again. Okay. So the logarithm is the thing that goes to infinity the slowest. Okay. This is something that we're going to be comparing things with when we get to chapter 11. Okay. All right. So typical problem in the book would be, for what values of p does this integral from 1 to infinity 1 over x to the p dx converge? Okay, now once we ask this question, and as soon as we answer it, we're going to need to remember it when we get to chapter 11, okay, because we'll be doing this similar stuff. Okay, well, just for starters, we know that it diverges when p is equal to 1, right? Okay, so the solution here, since we already know what's going on with p equal 1, we will remove that situation because we handled it directly. Okay, hold on. Mariana's one. Okay. Okay, so we'll do our thing here. We'll look at the limit. Look at the limit as t goes off to infinity of the integral of 1 up to t. Then it's going to be x to the negative p dx. Now remember, p doesn't equal 1, so we don't have to worry about a log interval. So this is going to be the limit as t goes to infinity of x to the negative p plus 1 divided by negative p plus 1 evaluated at 1 and t. Okay, so far so good. All right. So I'm going to switch the way this looks. This thing I'm going to write out here as 1 minus p, move it out, and then it's going to be the limit as t goes to infinity of x to the 1 minus p evaluated at 1 and t. So it's 1 over 1 minus p. Now that part isn't going to be making any difference, as we can see here, right? It's all coming down to this limit. So times the limit as t shoots off to infinity. So it's going to be t to the 1 minus p minus 1. Okay, now if I switch the exponent in there, 1 over 1 minus p, the limit as t goes to infinity, this is going to be, I have t to the 1 minus p, which I'll write as t to the negative p minus 1. So I'm going to flip this over to the 1 over t to the p minus 1. Okay. And then it's going to be minus the 1 over 1 minus p. Okay, so for this piece here, the limit as t goes off to infinity of 1 over t to the p minus 1. This limit is going to equal 0 if p minus 1 is positive. It's going to equal infinity if p minus 1 is negative. So imagine p minus 1 is negative 2. You'd have 1 over t to the negative 2, which is t squared. T goes to infinity. Okay, so our conclusion here from this conclusion is that the integral from 1 to infinity of dx over x to the p converges for p bigger than 1, and it diverges for p less than or equal to 1. In the equal to 1 case, we took care of manually. Okay, give you a second there. Any questions about that? Like a standard problem in the, in the textbook. All right, so there he goes with that. And all these guys. Now, I don't know how many of them you need to do, but they're just, they're integrals. In my book, the problems look like they're going from starting at number 5 and going to number 38. Okay. All right. So, and a very important improper integral is this guy. Okay. So, let's consider the following integral: 0 to infinity e to the negative x dx. Okay, so that's going to be e to the negative x evaluated at 0 and infinity. And I know technically we need to do the thing 0 infinity. Well, anyways, it's going to be 1 minus the limit as t goes to infinity of 1 over e to the t. And so that's equal to 1. All right, so this improper integral equals 1. All right. Now, just for us practicing purposes here, if I go from 0 to infinity, what if I put an x here? E to the negative x dx. Well, we're going to have to integrate this by parts, okay? U equals x, du equals dx, dv is e to the negative x, so v is negative e, negative x. Okay? So, what we have is uv, negative x e to the negative x, evaluated at 0 and infinity, and then plus the integral from 0 to infinity of this e to the negative x thing that we've already figured out was 1. Okay? So this is equal to 1 plus then the limit as t goes to infinity of x over e to the x evaluated at 0 and t. Okay, now what I did there is I got rid of the negative by flipping over the bounds. Okay, so this limit, of course, it's infinity over infinity, so it's equal to 1 plus the limit as t goes to infinity of t over e to the t. And L'Hopital, whatever, 1 plus 0 equals 1. Okay, now some interesting stuff starts to happen here, okay? If I try to do the x squared, 0 to infinity, e to the negative x dx, again, I'll have u equaling x squared, and du would be now 2x dx. dv is going to be the e to the negative x dx guy. So that means that v, negative e, negative x. Okay, so the integral is uv. So I'll get rid of the negative sign right now. Evaluated at 0 and infinity. Okay, and then plus 2 times the integral from 0 to infinity of x e to the negative x dx. Okay, now this thing is 0, this first guy, because e to the x, you L'Hopital it a bunch of times, and then this is going to be plus 2 times this problem that we just worked out ahead of time, and we got a 1 there. So the answer to this guy is 2. Okay, so what if I was to maybe do this with just any old positive exponent? So let's see what would happen. Okay, so let's let s be bigger than 1 for starters. We won't talk about fractions just yet. Okay, I mean proper fractions. And let's let this be the integral from 0 to infinity of x to the s e to the negative x dx. Okay. Now we already know that this is gamma. Okay. And we already know when s is equal to 0, it equals 1. When s is equal to 1, it equals 1. When s is equal to 2, it's equal to 2. So let's see. If we were to integrate this by parts, u equaling x to the s, du equaling s x to the s minus 1. Now remember, s is positive and bigger than 1, so s minus 1 is still going to be bigger than 0. And then our dv is going to be e to the negative x dx, and so v is going to be negative e to the negative x. Okay, so our gamma of s is equal to uv. Okay, so it's going to be x to the s divided by this e to the x, all evaluated at infinity and at 0, and then minus plus the integral from 0 to infinity, and I have an s here, and I have x, the s minus 1, e to the negative x dx. Okay, now again, it doesn't matter what the s is, positive, negative, whatever. E to the x goes to infinity the fastest. So that means that this whole piece is 0. And this is s, and that is precisely the definition of gamma of s minus 1. Okay? So this is our result for us that we've got. For s bigger than 1 real, obviously when I say bigger than 1, it's already implied that it's real. Okay, that gamma of s, which is this integral from 0 to infinity, x to the s e to the negative x dx satisfies the following things. Gamma of 0 equals 1. Gamma of 1 equals 1. Gamma of 2 was equal to 2. And gamma of s is the same thing as s times gamma of s minus 1. Okay? Here's what Andy just said in our group chat. You guys are going to feel pretty dumb if I get coronavirus and die. That will show you. What a moron.
Oh my God.
Only Andy. Okay.
I think at this point, you know, we're all gonna get it at one point or another. If we already didn't get it in the spring or towards the end of last year, we're gonna get it. It's inevitable.
Yeah. Next door neighbors, he tested positive on Saturday.
Oh,
Okay,
really?
so look at what this is kind of close to. Okay. 0 factorial is 1. 1 factorial is 1. 2 factorial is equal to 2. N factorial is the same as n times n minus 1 factorial. Okay, so Euler, in a sense, extended the domain of definition of this factorial function. Okay? All right, now, so like, for example, you can actually just see it here, you know, gamma of 4. According to this, it's going to be 4 times gamma of 3. And according to that, that's going to be 3 times gamma of 2, which we worked out to be 432, which is 4 factorial. Okay, so an observation that we can make, or a result for us, is that with our gamma function defined like this, 0 to infinity, x to the s, it's gamma of s, not x, gamma of s, x to the s, e negative x dx. Okay. That gamma of n is equal to n factorial for all n in here. Okay, so what Euler was giving us was sort of like a way of figuring out, like, what would be 1.5? The concept that we're trying to copy here is 1.5 factorial. Okay, well, Euler just sitting around thinking one day, saw all this in his head and just, you know, kind of did that. Okay, so now this is the classical gamma function. Normally what you see here is that in your next textbook, and I was just in my office, I should have grabbed that engineering textbook, but when you see this thing, it'll be in your math for engineering majors.
185, I believe.
Yeah. Hold on a second. Okay.
Your volume is off again.
Yeah.
There you go.
There we are. I got to go back to the screen. Okay, that. Back to that. Okay, so this would be x to the square root of 2 e to the negative x dx. Okay. Now, the way that this works is the square root of 2 is bigger than 1, right? Now, according to you know, this result up here, that gamma of the square root of 2 is going to satisfy gamma of the square root of, whoops, it's going to be the square root of 2 times gamma of the square root of 2 minus 1. Okay. And so, let's get to that right there. Okay, so if it's a fraction, like properly in between here, so no matter how big of a number you give me that's not an integer, 872.4. If I wanted to figure out gamma of 872.4, it's eventually going to get me a bunch of numbers, some big ass number, and then down to gamma of 0.4. Okay. So let's look at an S that's in that interval. Okay, so let S be in the interval from 0 to 1. It's a proper fraction. And we're going to go 0 to infinity. This is this gamma of S thing. And it's going to be x to the S e negative x dx, same definition. Okay. Okay. So if we do our parts thing again, we're going to let u equal x to the S and dv equal e to the negative x dx. Du is again our s x to the S minus 1. Okay, now remember, S was between 0 and 1. So now S minus 1 is negative. V is negative e to the negative x. Okay, so again, I've got my S between 0 and 1. The gamma of S is going to be uv. So that's going to be x to the S over e to the negative x, evaluated at 0 and infinity, plus S times the integral from 0 to infinity of x to the S minus 1 e negative x dx. Okay, now again, well, that's not negative x down there. That's x. Again, this whole thing goes to 0. Okay, and so what we're left with is the gamma of the S is going to be S times this integral from 0 to infinity. Now it's x to the S minus 1 e negative x dx. Okay. Okay, now this looks exactly the same, right?
Yeah.
But you have to kind of follow the subtleties here. Way above here, like up here in this one, remember S was positive, right? So the only thing that's making this an improper integral is that. Okay. Now, because S was between 0 and 1, S minus 1 is negative. And so this is improper because we are not continuous at x equals 0. Okay? All right. Now, so what you're going to do here, and tables of these things, you know, were created. Like for me, like I look at the Kreisig engineering book, and you've got these tables of these things. Now with the phones and everything, you can get these things pretty quickly. Now I'm doing a fairly extensive treatment of this gamma function for reasons that are going to come in chapter 11. Okay, I'm going way beyond the scope of anything I would test you on. So I'm just, you know, basically for the math majors and stuff. And these are all improper.
So,
okay. Yep.
A question real quick. So if e to the x was, if it were e to the negative x, it would have not gone to 0. It would have gone to infinity if it were negative.
You mean you're talking about the exponent here?
Yeah. No. Yeah.
If that was positive x, it would go to infinity. E to the x dominates everything.
Okay.
Okay, but it's that negative.
Okay.
Okay, so what we've got here is that s minus 1 is a negative number. Okay, so what we need to do is consider now, instead of, so what we're seeing here is that you pick a number that's not a positive number, that's not an integer. Eventually, you're going to be doing the recursion relationship so much that eventually you'll get down to the one case you're going to do. Okay, and eventually you have one last integral where the exponent up here is positive, and then it goes negative. Okay, so let's look how to deal with the negatives. So let's consider S living in here. Suppose S lives between -1 and 0. And we're going to once again try to figure out how to define this. Now, what I was going to say earlier was that the reason I'm doing this is for a handful of you to be able to reference. Most of you aren't mathematically mature enough to know where to look for results, meaning you just haven't been exposed to enough math. Basically a bunch of algebra, trig, and some calculus, right? There's a lot more out there. And if you look up on Wikipedia, what happens is they give you this thing, and then they start talking about S being a complex variable, and then they talk about the zeros of the complex function. And so it starts to get out of hand, you know, like it's somebody's PhD thesis. Okay. Now, in this situation, because the S is negative, when we do integration by parts, we're going to do the reverse order. We'll let u equal e to the negative x and dv equaling x to the s. So that du is now negative e negative x dx, and v is x to the s plus 1 divided by s plus 1. And so our gamma function is going to be uv. So it's going to be x to the s plus 1 divided by s plus 1 e to the x evaluated at 0 and infinity and then plus 1 over s plus 1, the integral from 0 to infinity of x to the s plus 1 e negative x dx. Okay, so again, when this is going off to infinity, it starts at the 0, that's giving that 0. So this whole thing is going to 0, is 0. Okay, so what we found is that for s between -1 and 0, like that, the gamma of s is going to be 1 over s plus 1 integral 0 to infinity x to the s plus 1 e to the negative x dx. Okay, now what's important about this is that s plus 1 is now sitting in between 0 and 1, right? And so if you go and compute a bunch of these things and you compile them in a list, you know, that's what you got. Okay, so let's see. Let's try one of these. Okay, let's see if we can trick the system somehow. Okay, so for example, let's see if we can compute gamma of -1/2. We basically are trying to figure out what -1/2 factorial should be. Okay. All right, so our gamma of -1/2 is the integral. Okay, now the story here that is being told is important for some of you, but these integrals that I'm doing are important for all of you. So hopefully you're, you know, following along and integrating as best you can. Okay, so the gamma of 1/2 is going to be x to the -1/2 e to the negative x dx. Okay. All right. So let's write it like this: 0 to infinity, 1 over the square root of x e to the negative x dx. All right, so now I'm going to do a variable substitution. Okay, so suppose that x, oops, x equals y squared. This is like saying x equals sine of theta. Now you're going to have to do what dx is. Dx is going to be 2y dy. Okay, and when x equals 0, y equals 0, x equal infinity, y equals infinity. Okay, so by doing this substitution, we get this: the integral of the square root of x, which is going to be 1 over y, and then this is from 0 to infinity. Now notice that it's improper right there, right? We pointed that out. Okay, then it's e to the negative y squared times 2y dy, which is 2 times the integral from 0 to infinity of e to the negative y squared. Okay. Now, In chapter 11, we're going to learn a way of figuring out an infinitely long sum for this, okay? And then we'll be able to actually make some headway with this. Okay, now here comes the big trick. Big trick. If gamma of -1/2 is equal to 2 integrals from 0 to infinity of e to the -y squared dy. And you're going to watch me evaluate this integral right now. Then the gamma of 1/2 squared would be this integral times itself. Okay. Got it? Okay, now remember that these are just numbers. Okay. So it's just a number. So what do you say? I switch the variable on the inside back to x. 0 to x of e to the -x squared dx. I can do that, right? It's just a number. Remember, in the integral, you can use any letter that you want. To integral from 0 to infinity of e to the -y squared dy. Okay, now Calc 3 stuff. I don't generally like doing this, but it's not that far of a thing to do. So there is a theorem due to Frobenius that says that the product of those two integrals, and you'll learn this for you guys that are going into 280, almost as soon as you start doing the integrals. Okay, you're going to have to do some other stuff first, like gradients and vectors. Okay, but what we're going to see here is it's going to put this 4 out here, and then it's the integral from 0 to infinity, and then another integral 0 to infinity e to the -x squared e to the -y squared dy. This is called a double integral. Okay. Now the theorem says that as long as it's a definite integral going from a to b and all that stuff, the order you can do this. Okay, so now this is where, if you're really going to over the weekend get to look at this stuff, there's a dy and also a dx. Actually, the way that I have it written, it's dx dy. And we start talking about, is that really a product of something? Well, what we call it is like dA. Okay, but it's not really a product. Okay, so what this is 4. Now I got this double integral. And this is e to the -x squared plus y squared, then dx dy. Okay, now I will end up switching to polar coordinates. And with that, x squared plus y squared equals r squared. And it turns out that dx dy, you'll learn this fairly rapidly, r dr d theta. So what this goes is 4. Okay, now we're in polar coordinates. So it's going to be e to the -r squared r dr d theta. And the r is now allowed to go from 0 to infinity. And the theta is going to go from 0 to pi over 2. Okay, now that's a discussion that we will have later. But anyways, I wanted to just complete the problem for you to give you an answer.
So real quick over here, where you had 4 to the radical integral of pi going, infinity going to 0.
Right here?
Down below that.
Right there?
No. Well, it's that line, like above that line, little line that you made. Shouldn't it be e2 to the e minus, because you had 2 e's above it.
Right, and so I used the exponent rules.
Oh, okay.
Okay. All right, so this is a little trick that you'll learn when you get to math 280. But we were so close to figuring out the factorial of something that, come on, I just didn't want to pass it up, you know. Okay, so here's what we found here is that, whoops, that's the answer. This integral ends up equaling pi. And so gamma of -1/2 squared equals pi. That means that gamma of -1/2 is going to be the square root of pi. Okay? And for that matter, if you scroll clear all the way back up here, it would appear to me, if I go way up here, okay, that 2 times the integral from 0 to infinity of e to the -y squared dy, right up there, okay. Since the gamma was of that is just this one, this is going to equal the square root of pi. And so that says that the integral from 0 to infinity of e to the -x squared dx is going to be the square root of pi over 2. And so hopefully maybe you can remember this now. If I go from -infinity to infinity of e to the -x squared dx, it's going to give us the square root of pi. Okay, so getting into the gamma function helped us with that. All right, so later on when we get into the chapter 11 stuff and the zeta function, we'll make the connection. Okay, some other things that are going on in here. Some more results that maybe just need to be written down. If, let's say, 0 is less than or equal to f less than or equal to g for all x, and if the integral from a to infinity of g of x dx converges, this implies a to infinity of f of x dx converges. Okay, so it's like squeeze theorem stuff. All right, so like the example of this is this thing. If I'm going to go from 0 to infinity, and I'm going to have sine squared x over 1 plus x squared dx, is it going to converge or is it going to diverge? Well, we make the observation here that sine squared x over 1 plus x squared is no bigger than 1 over 1 plus x squared. And so the integral from 0 to infinity of sine squared x over 1 plus x squared dx is less than or equal to 0 to infinity of dx over 1 plus x squared. And that was tan inverse of infinity. That's the pi over 2. That's finite. So this integral converges. Okay, now it's very important for you guys to understand what's being said here and what isn't being said. This thing converges. It does not converge to this number. This is the bound. This is the thing that this guy converged to. All we can say about this integral is that it converges. Okay? All right, so we'll be having more fun with all of this. So now we need to talk about when we want to do the first exam. You guys feel confident?
Only a little.
Like, when would you want to take it? Tomorrow?
I would say probably like Thursday.
Well, tomorrow is Thursday.
Oh, I thought that we were going to do it next week.
Yeah, well, you know, I mean, these things aren't going to be that hard. Okay, so let's do it next week, like on Tuesday. Monday, I'll give you, that'll be over the weekend. If you come up with questions, you know, ask me or just email them to me and I'll do them. Okay. Now, what's going to be on the test? Well, it's going to be a whole bunch of integrals. Okay. So there'll be maybe, you know, one of these approximation questions. I won't ask you any gamma function stuff, but just a bunch of integrals. And so over the weekend, there's no secret now that we can't go to the beach and get drunk, you stay home, get drunk, and do a bunch of integrals. Okay.
Thank you.
All right. What else you guys got? Any other questions?
So how was it meeting the girl from the Happy Days? I can't remember her name.
Oh, Wonder Years?
Yeah, Wonder Years. There you go.
Yeah, I'll tell you about her in a second. Let's take a break. I've been kind of sitting here motionless for a while. I need to use the restroom. All right.
People in the commentary are like, no, we can't. He told us like a few that could be possibly in the test, but it's going to be a lot of integrals. Like, so if you've been doing a few of them at home that are hard, they're not going to be like ridiculously hard. They're not going to be like ridiculously super big numbers.
Eduardo,
Yes.
did you plan to, like, did you figure out who, like, which professor you will take? But the next, it's Calc 3, I think. Yeah. With?
Yeah, there's Calc 3, but I couldn't find a professor that I like teaching it for the fall.
Mm-hmm.
And it's a lot. To me, it's not like I kind of would like it if he would teach it, but I don't know if he is. I'm taking physics 1.
With who?
With I can't remember his name. Let me check.
Is it Abbas Faridi? No.
Yeah, it's that one.
Okay, you are with me.
I didn't see anything bad posted. I think it's a new professor, but I've always had good Indian professors that explain things really in depth, and I think they're awesome.
Mm,
I think Faridi's Persian.
yeah. Yeah.
Yeah.
Actually, yeah.
I don't know.
Persian. It's per not Indian.
Oriental people usually have the best way of teaching some math. And I think
Bobby, aren't you planning to teach Calc 3 next fall?
No, in the fall I have 170 and 180.
Oh, okay.
They've already, Tim already makes the schedule. I can't do 280 until they decouple it from honors.
285.
I'll do 285, you know, when you guys get there, and maybe, but who's doing 280 in the fall?
Maybe, yeah. It's hard to find that professor.
Yeah.
I think there is only one professor for in the fall, like in OCC.
Yeah, it's only one professor for the fall.
Yeah.
Well, here, let me look.
Honors.
I can look up here and see.
Hey, Bobby, are we allowed to take the test early, like on Monday?
If I put it up in time.
Okay.
Why? What's going on Tuesday?
Oh no, someone asked in chat if they can take the test early, but their mic doesn't work. Or no. Yeah, someone asked if they want to take on Monday.
I don't want to do it on Monday because I want you guys to be able to ask me questions. Okay, here I'm looking up fall, and then I'll look up math. Wonder who our new person. Yeah, we have a new person. She was hired to teach the support classes. Let's see. And Andy, I now have corona in my lower back. Let's see, 280. I haven't even looked at this in a while. I'm almost full there. Jeez. Okay, so 280, your choices are Stanislav or Doug Lloyd or Mariana. That's it. I think that's 3 pretty strict people. That's what. So I can tell you that Stanislav is not Bobby. He's the one that's every time we have a meeting, he's talking about, oh, I'm gonna figure out a way to catch these cheaters yet. Give up, dude. You know,
So Bobby, about the taking test early, is it possible to do it early in the morning? Like early Tuesday morning?
Oh, just like post it and have it out there?
Yeah.
Well, I want to do it timed.
Oh, okay.
Because as a department, we all agree, you know, let's try to make this as normal as possible. So at least for like, let's just say we tried it, you know. Now, if you have technical issues and stuff, I get it, but as long as like on record, like I'm doing the test and it's timed, you know.
All right.
Because everybody seems to think the reason I'm so popular is because all of my tests are take homes. Okay, well, you guys know that's not true. One of them's a take home.
One of them.
Okay, but now they're saying, well, it's because you're not even monitoring their tests. Well, are you? You know, no one is. You know, so. But my Math 30 class, they're kind of interesting. You know, I gave them the time test, and one girl, she just cannot figure out how to load this thing back up. And I don't know what to tell her. But you know, they missed some things on their exam. Okay. By the way, if you guys want specific stuff in the chapter 7.8, which is the improper integrals. I will go through here. In my book, number 71 is the definition of what's called a Laplace transform. Okay. So look up that problem. I can get it in the chat now. So the exam posted and due 8:30 to, yeah, everyone. 8:30.
What version of the book do you have?
I have, this is the 5th edition. What edition do you have?
The 8th.
Okay. Well, you can just look for the word Laplace transform. These are going to be a part of your future. If you take Andy for 285, he covers Laplace transforms there. I just choose not to do them because I figure when you get to them, you'll get to them. Let's see here. 75 looks kind of interesting. Let's see. Number 65 is the Earth's escape velocity. Maybe that'd be interesting for you to look at. I don't know. So there we go. All right, well, I'm not going to do anything new because I figure, you know, we still got tomorrow. And I learned my lesson last semester. One day I just lectured for 2.5 hours in 285. And I mean, I can hear it, you know, when Brian's in the class. Like, I'm just copying. I don't even understand any of this shit. So I'm going to go slow. No, you don't need to show your work on the exam. You're just going to have the exam. It's going to look like, let's see if I have one. I have like my math. So here's what I gave my math 30 class. Oh.
We can't see.
Oh, I gotta turn my thing back on. So for you new people, you know, my test just this is what they always do. Okay. And so then you'll like put your answers on it and then, you know, scan it back. All right. Does it keep stopping the video? Kind of strange. Participants 47. I got another chat in the room. Chat. There we go. Okay. All right. So integrate tonight, everyone. Got it?
Thank you.
You're under orders. You have to integrate tonight. All right. And tomorrow, so if we just take a picture of the answer and upload it on Canvas. Yeah, that's how it's going to work. And even if you're late turning it in, you know, I get it. I'm just trying to like make an attempt here, you know. All right, guys. So email me tonight or tomorrow when you have questions about anything. All right.
Thank you.
Mullen. And tomorrow we will get into chapter 8 and we'll start talking about arc length and stuff like that. All righty, everyone. Have a great rest of your night.